Fountains of diamonds that erupt from Earth's center are revealing the lost history of supercontinents. Diamonds seem to reach Earth's surface in massive volcanic eruptions when supercontinents break up, and they form when continents come back together. In the twilight of the Cretaceous, 86 million years ago, a volcanic fissure in what is now South Africa rumbled to life. Below the surface, magma from hundreds of miles down shot upwards as fast as a car on the highway, and if that car were barreling through solid rock, chewing up rocks and minerals and carrying them towards the surface in a reverse avalanche. And what this looked like on the surface is lost to history, but it may have been as dramatic as the eruption of Mount Vesuvius. What it left behind was a series of carrot-shaped, igneous rock-filled tubes under low, weathered white hills. In 1869, a shepherd's discovery of a huge sparkling rock on the nearby riverbank would catapult this unassuming landscape into infamy. The rock was an enormous diamond that would eventually be known as the Star of Africa, and the White Hills hid what would become the Kimberley mine, an epicenter of South Africa's diamond rush, and quite possibly the largest hole on Earth ever dug out by hand. Thanks to the Kimberley mine, often called the Big Hole, the formations where diamonds are found and are now known as Kimberlites. We do have kimberlite volcanoes in the United States. A lot of them are, I think, in the Midwest. Okay. Now, the formations are sparkling across the globe, from Ukraine to Siberia to Western Australia, but they're relatively small and rare. What makes them special is that their magmas come from very deep down. There are still questions about precisely how deep, but they're known to arise from beneath the bases of continents and the border of the hot convective mantle. Some originate even deeper and the transition between the upper and lower mantle as well. And as such, these magmas tap into very deep, very ancient rock, and they interact with other processes that occur only in the deep earth, namely the formation of diamonds. To crystallize plain old carbon into hard, sparkly diamond requires great pressure. So these gems form at least 93 miles down in the deepest layers of the lithosphere. The scientific team, the term for the crust and the relatively rigid upper mantle, some known as sublithospheric diamonds, form even deeper, down to around 435 miles. Kimberlites, on the eruptive journey to the surface, catch diamonds and drag them into the upper crust, delivering them relatively unscathed and sometimes even containing pockets of fluid from the mantle itself. Researchers have long known as the tectonic plates grind under one another, they drag down carbon from the surface to depths where it can crystallize into diamond. And now they're starting to see that what goes down must sometimes come up, and that this reappearance of carbon, now pressed into glittering gems, diamond that is also tied to the movements of tectonic plates. In particular, diamonds seem to erupt when supercontinents break apart. And while these are different processes, together the diamonds and kimberlite can inform us about life cycle of supercontinent times, said Suzette Tummerman, a geologist at the University of Bern in Switzerland who studies diamonds. Coming to the surface, no one has ever seen a kimberlite eruption firsthand. There have been very few in the past 50 million years, and the most recent possible eruption in the Igwisi Hills of Tanzania occurred over 10,000 years ago. Not only that, but the main material in kimberlite, the mineral olivine, weathers away quickly on the surface, said Hugo Oleruck, a research fellow at Curtin University in Australia. This makes studying kimberlites challenging. Scientists are perplexed, for example, about the chemistry of the original source of the melted rock in the mantle, as well as about how kimberlites managed to punch through the stable cores of what geoscientists called cratons, the thick interior parts of continents that usually resist disruption. A handful of recent studies are sketched out the new examples, explanations of why this happens. The first clue is timing. It's long been noted that pulses of kimberlites activity seem to correspond with the approximate timing of supercontinent breakup, said Kelly Russell, volcanologist at the University of British Columbia in Canada. A 2018 study led by Sebastian Tapp, a geoscientist at the Arctic University of Norway, took a global look at this coincidence of timing and found that it was a spike in kimberlite eruptions around the breakup of the supercontinent Nuna some 1.2 billion years ago to 1 billion years ago. Another pulse occurred between 600 million and 500 million years ago, coinciding with the breakup of the supercontinent Rodinia, according to a 2018 research, followed by a smaller pulse between 400 million and 350 million years ago. But the most prolific period, accounting for 62.5% of all known kimberlites, occurred between 250 million and 50 million years ago. That range happens to coincide with the breakup of the supercontinent Pangaea. To some researchers, this suggests the supercontinent cycles are crucial for kimberlite eruptions. The breakup of these continents are fundamental to getting these diamonds up from deep depths, Oleruk told Live Science. Oleruk and his team recently analyzed the ages of unusual pink diamonds from a formation in Western Australia and found they likely came to the surface about 1.3 billion years ago, within the window of Nuna breaking up. The new discovery links diamonds to the stretching of continental crust, Oleruk said. It's those extensional forces that allow those little pockets of deep-seated magma to rise to the top, he said. The tricky question, though, is how this happens. To get kimberlite, there are two key ingredients: deep melting rock rich in fluids and a continental disruption that may bring the melt to the surface. No one knows what causes the formations of the kimberlite melt, but the chemistry of kimberlites is very different from that of the mantle rock it melts from. Kimberlites are also rich in volatiles such as water and carbon dioxide, which is what makes them so buoyant and high velocity. They shoot through the crust like champagne rushing through the uncorked bottle, ascending to up to 83 miles per hour. For comparison, the magmas that flow out of the volcanoes in places like Hawaii max out at around 13.5 miles an hour. An August 2023 study used computer modeling to figure out how kimberlites can burst through the thick hearts of continents. The researchers found that the process of rifting, in which continental crust pulls apart, was key. The stretching creates peaks and valleys at both the surface and base of the continent. At the base, these jagged edges allow warm mantle material to rise and then cool and fall, creating eddies. These eddies mix material from the base of the continents, making the frothy, buoyant kimberlites, which can then shoot up towards the surface, carrying any diamonds that may happen to run into their way up. This process, again, began right where the continent was rifting apart, but modeling showed that these jagged regions of eddy formation destabilized neighboring areas on the craton, creating the same dynamics closer and closer to the continental interior. The result was a pattern of kimberlite eruptions starting near the rift zone, but gradually marching into the areas of stable crust. This slow march explains why kimberlites pulses don't peak until a bit after a big breakup begins, said Thomas Gernon, geologist, University of Southampton, the UK, who led the study. You will see these peaks of kimberlites seem to happen after big supercontinents have broken up, he said, but it's not just a one-hit thing. It's something that may last quite a long time after the supercontinents break up. Kimberlites may be quite common at the bases of continents, said Tapp, whose 2018 study on kimberlites and supercontinent breakups came to a similar conclusion as Gernon's. Tapp and his team found that these melts may have been particularly prominent during the breakup of Pangaea because the mantle, which has been slowly cooling since Earth solidified, reached just the right temperature around 250 million years ago to have kimberlite-type melts dominate. Prior to that period, the rocks in that region may have been too hot to get that combination of melt and volatile material that makes kimberlites so eruptive. This may be one reason why most kimberlite diamond mines date from the breakup of Pangaea. The messages in the diamond, as the dull white hills that once covered the Kimberley mine attests, kimberlites themselves cannot say much about the mantle where they originated. They weather away within a few years, losing much of what makes them interesting on a chemical level. However, the diamonds carried within kimberlites are a different story. They have their own formation histories that don't coincide with the formation of the kimberlite magma itself, but their chance meetings hundreds of miles below the surface mean that bits of the mantle that would never otherwise see daylight can reach human hands. These bits are microscopic pockets of fluid from the time the diamonds were formed. Many of these inclusions date back hundreds of millions of years, while a few specimens count their ages in the billions of years. Plus, some of these diamonds form very deep in the mantle, so certain stones can carry materials from as far down as the boundary between mantle and the core. Only in kimberlites can we see samples coming from 250 miles down or even 1,200 miles down, said Maya Kopilova, professor of diamond exploration at the University of British Columbia. No other magmas on Earth do that, she said. While the eruptions of diamonds can trace the story of supercontinent breakups, their formation may also provide a clue to how continents come together. In a study published October 2023, Timmerman studied diamonds from Brazil and Guyana that formed between 186 and 434 miles deep. By dating fluid inclusion within the diamonds, Timmerman and her colleagues estimated that the diamonds formed around 650 million years ago when the supercontinent Gondwana was forming. The diamonds probably stuck to the base of the continent and sat there for millennia until Gondwana broke up during the Cretaceous period and kimberlites brought them to the surface. What was important about these super deep diamonds, Timmerman said, was that they helped explain how continents grow. Supercontinents are built when oceanic crust pushes under continental crust. This process, called subduction, tugs two continents on opposite sides of the ocean closer together. This same subduction brings carbon to the depths where it can be compressed into diamond. Down in the mantle, bits of these subduction plates can become buoyant, raising back up, carrying super deep diamonds with them. This material may stick to the base of the continents for millennia, helping them grow from below, and it may also explain how super deep diamonds land in a place where a kimberlite can catch them. Now, ancient diamonds may also tell us about other milestones in Earth's chaotic history. Some diamonds are forged from carbon that was incorporated into Earth upon its formation, while others form from carbon from ancient life dragged down with slabs of subducted crust. It's possible to tell which process formed the diamonds by analyzing the molecular structure of the carbon within diamond inclusions. These inclusions can thus hold secrets about hazy numbers in Earth's history, such as when widespread subduction began or when life in the oceans became prevalent. But to get those answers, researchers will need to get a better figure of how old diamonds are, and they'll need more diamonds that are both ancient and from the deepest depths. Going back in time, supercontinent breakup and the ones before that, Ollier said, I strongly suspect that there's still lots to be discovered. This is by Stephanie Pappas on Life Science. Please leave your comments and thank you for your support. My Patreon account, the daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.